Welcome to part 3 of chapter 10. We're going to keep talking about our thermodynamics state functions, and in this video we're going to introduce Gibbs free energy. So we've dealt with enthalpy, which is a capital H, entropy, which is a capital S, and Gibbs free energy, which will be a capital G. It is a state function, meaning that it doesn't depend on path, that can actually be used to predict the direction of spontaneous change. So we can use Gibbs free energy to determine if a reaction or process is going to be spontaneous in the forward direction. Now, why is this is so useful? It's going to combine delta H and delta S, which we already know and have a little bit of intuition are at least connected to spontaneity. In general, we see a negative delta H, right, an exothermic process, as being favorable, because in an exothermic process, we are going to wind up with products that are lower in energy. But for every rule, right, there's an exception. There are definitely spontaneous endothermic reactions. So while delta H is going to play a role in spontaneity, it's not an exclusive determinant. Delta S, we also know, is connected to spontaneity. We see delta S positive, right, an increase in entropy, as being something that's favorable, right? So these two sign conventions we say are favorable. But the opposite, there are going to be examples. There are going to be examples of spontaneous processes like water freezing at cold temperatures, where delta S is going to be going down, but that is spontaneous. So spontaneity must be a little bit more complicated than that, right? And that's where Gibbs free energy comes in. Gibbs free energy is defined, and we're going to look at change in Gibbs free energy because we're always interested in the change that occurs during some sort of process. It is going to be defined as delta H minus temperature times delta S. We're going to see that temperature plays a pretty significant role in spontaneity for some systems. The sign convention that you must know is that delta G, negative delta G, is going to be a spontaneous process. So let me write that in a different way. Delta G is going to be less than 0 for a spontaneous process, right? So if delta G is positive, that means it's not going to be a spontaneous process. So what is going to factor into the sign? Well, we know that an exothermic reaction would give us a negative delta H, right? And that's going to contribute favorably mathematically to delta G. And then we're subtracting delta S. So a positive delta S will contribute favorably as well. And temperature is going to be a determinant when enthalpy and entropy are sort of conflicting with one another. So a chart that is going to be important for you to understand and is going to kind of summarize what you're seeing on these slides looks at the sign conventions and the implications. So if we have a reaction that is both exothermic and increasing in entropy, it's going to be spontaneous at all temperatures. Right? So always spontaneous. Right? Because you're going to have a negative delta H and you're going to be subtracting a positive delta S. Temperature will always be positive because temperature needs to be in Kelvin. So if you have a negative delta H and a positive delta S, delta G can only be negative. So it'll always be spontaneous. On the flip side, if you have an endothermic reaction that is decreasing in randomness, right, decreasing in entropy, this is never going to be spontaneous. No matter what the temperature, no matter what. That is a process that is going to always need constant intervention to go forward. But what about when our enthalpy and our entropy are at odds? If we have an exothermic reaction, but one that is decreasing in decreasing in entropy, right? It's getting more orderly. Then it will be spontaneous at low temperatures, right? That's going to be when delta H is going to be larger than this factor here of T delta S. So let's think of an exothermic reaction that's spontaneous only at low temperatures. Water freezing to ice, right? That is something that is exothermic. It is decreasing in entropy of the system, and it is spontaneous, but only if you are at or below the freezing point. What about if we have an endothermic process that is increasing in entropy? This is going to be spontaneous only if the T delta S can overcome delta H. So only spontaneous at relatively high temperatures, right? Low T and high T are relative terms, and they're really just telling you a threshold. So something that is endothermic but might be spontaneous at high temperatures would be the reverse of what we were talking about before, ice melting. We know ice melts, and that's what we're being asked to explain here. Why does ice spontaneously melt in a room temperature environment, but if you go outside when it's freezing, it doesn't melt, right? It's endothermic either way. To get the ice to go from solid to liquid, we have to input energy to overcome intermolecular forces. It's getting more random because now the molecules can slip and slide past one another, and there's going to be more microstates. And so we can see an example that we're familiar with of the last combination in the chart here. Right? Yes. Delta H is positive, but so is delta S. And so at the high temperature, right, at the melting point, that is when this will be spontaneous. Now, something that we need to know here to answer the next question is this is an equilibrium that we're talking about here, right? We're talking about solid going to liquid, and at high temperatures, it's spontaneous, but the reverse would not be, right? Liquid going to solid would have to be at a different temperature. When these two are in equilibrium, delta G equals 0 at the melting point. Right, when you've got an equilibrium of that solid and liquid right on the dot of the melting point. So, given that little tidbit of information, let's see if we can estimate the melting point of polyethylene. We're given delta H and delta S, so before we plug those in, let's think about delta G, right? It equals 0 at the melting point, so that's going to be 0 equals delta H minus T delta S. Now we know delta H and delta S. We want to solve for T. So I'm going to rearrange this. With 0 on this side, there's only one variable for us to solve for. T is going to equal delta H over delta S. All right? And then it's just a matter of plugging in. Something that you want to note, and it's something that I'm sure you really and truly miss me saying over and over again, but pay attention to units. Look at this. Delta H is 7.7 kilojoules per mole divided by 19 joules per mole Kelvin. All right, well, moles will cancel out and Kelvin will be on the top, but kilojoules and joules do not cancel each other out. So you need to convert one of them. So I'm going to go ahead and just multiply that numerator by 1,000 because I know there's 1,000 joules in 1 kilojoule. And now kilojoules cancel out, joules cancel out, and all I'm left with is 1 over Kelvin, which is Kelvin. This is going to result in a temperature of 410 K. Now, it's not perfect. It's an estimation. This assumes that delta H and delta S are not affected by temperature differences, which they are. So that's why you're going to see words like estimate, estimating that melting point. Now, before we move on, I do want to talk for a moment here about free energy and work. Free energy, this Gibbs free energy that we're calculating, it tells us about spontaneity, but it also tells us the maximum amount of work that can be done by a system. The sign with that negative is in there just to match the sign convention of delta G. But rarely do we ever get the maximum amount of work from a system or process. And that's because to get the maximum amount of work, you need a reversible path. So that means that we're not going to lose any waste energy. Usually that requires that you make very, very small incremental changes and that your system could be returned to its starting point unchanged. Most of the reactions we're looking at are not going to be close to an equilibrium, and they are going to be considered an irreversible change. You burn a gallon of gas, that is not considered a reversible change. It would be very hard to get the CO2 and the water to react to give us gasoline. All right, and so what we typically see is that actual work available winds up being sometimes significantly less than the maximum amount of work available. Let's see if this pencil will last me the rest of this video. But at least with delta G, we can estimate what the absolute max is we could do with a system. Now, for this last little bit, we're gonna look at delta G being a state function, and we're gonna solve a problem. This equation that you're about to see ought to look very, very familiar to you now. Delta G naught is going to be at standard state, right? 1 atmosphere, 1 molar concentration. It's a lot more, we're going to see something similar to delta H of formation because we can look at delta G of formation, right? That's going to be defined in very much the same way as delta H of formation. We're looking at the formation of a compound from its constituent elements in their standard state. So, because it doesn't matter how we get from start to finish, just matters, right, that the start and the finish are in the same place, we can use these delta G's of formation to calculate delta G of a reaction. So what I want you to do is ignore all the weirdness there. This is the equation we're using. If you downloaded the online notes, your version should not have that problem. It was when I opened it up in this drawing app. But this should look very familiar to you at this point. We are taking the delta G of formation of the products, so all of the energy change, right, or free energy of forming the products from the elements, minus essentially the amount of energy it would take to break the starting materials down into the elements. So you notice H2 here is 0. Well, that's because H2 gas is the standard state, right? So the change in Gibbs free energy of getting H2O gas from H2O gas is 0. Now, we have the same little hiccups here. This 4 should be a plus sign, and this 4 should be an arrow. We're going to just go ahead and we're going to plug and chug into this equation, right? We have 1 mole of butane times negative 15.71 kilojoules per mole. That's the only product. And then we're going to subtract 2 moles of our ethene up here times 68.12 kilojoules per mole. You could write out the plus 0, but mathematically it's just plus 0. And what we find is that Gibbs free energy, once we finish this problem, oh no, hold on. I guess we're just going to calculate this here together. That's fine. Oh, there we go. Pardon me. Let me tell you a joke while I pull out my calculator. What do you call a fish with no eyes? Please talk amongst yourselves as you figure this one out for me. Negative 15.71 minus 2 times 68.12. All right, I got negative 151.95. I'm going to double check that really quickly while we're still thinking about that fish. Yep, that seems reasonable. A fish with no eyes, ladies and gentlemen, is a fish. That is my favorite joke because I am a child. All right, negative 151 kilojoules. Now that is the change in Gibbs free energy, but what does that tell us? That negative value tells us that this is spontaneous. All right, the forward process is indeed spontaneous. And that is the last little bit of chapter 10. I will see you in a few days in chapter 11.